È vero.
No,
non so se
uno di loro che è maschinoso, un po' di
Ci siamo. Siamo partiti.
Ok. Allora, lo speaker di oggi è Fabio Cumbo. Fabio ha passato diversi anni qui da noi nel corso del PhD. Fabio è un software engineer e ha un PhD in Computer Science and Automation Engineering e attualmente è un postdoc, ha una posizione di postdoc presso il Center for Computational Life Sciences Lerner Research Institute della Cleveland Clinic. E oggi ci parlerà di questo lavoro, Towards Revealing the Hidden Diversity of Microbial Matter and its relation host health and environmental factors.
Thanks for I think we should switch to English so that my introduction better understand well, I will skip the presentation. You actually introduce me. So let's move on. I will talk about actually the framework, a software framework for the analysis of the so-called microbial dark matter. So all those still unknown, yet to be named microbes. So we are talking about microbial genomes. So let me start with a brief introduction of the human microbiome. And I usually start by saying that it's clear to most of the people now that if you want to study human health and of course human diseases, we cannot only focus on our own cells, but we have in many cases we have to consider the microbial component, as we can call it. So what is our microbial component? It's the set of microbiomes, not only the intestinal microbiomes, but also the other human microbiome, the skin microbiome, the urogenital tract microbiome, for example, and they all represent important functions for our body. So functions that some of them are listed here, and they go from helping us digest food, or training our immune system, or helping with our metabolism. Or even the gut-brain axis, so really having an effect on our body in different, on multiple levels. We don't know a lot actually. We don't know what is the extent of the interactions between the microbiome and the different aspects that we just mentioned. But it's really something that we need to look inside much more. The human microbiome is not only bacteria, it's something you should think about. We have viruses, eukaryotes here. This is all an extremely complex community that again we need to take into account. We can give some numbers to give an idea. The estimates are now that there are at least the same amount of microbial cells than human cells. Of course, microbial cells are way smaller. And this will account for around 1 kilo inside us. But numerically, it's really a lot, right? So I think that what is even more striking here is that if you think about the function, the biomolecular function that it can bring to us, with different genes and gene families, that it can bring to our body, these numbers are way more unbalanced. So there are way more functions, way more molecular functions that are brought by microbial genes compared to our own 20 or 25 genes or so, the human genes. So results in this field improve the real recently, but it has been centuries that actually scientists knew by the microbiome was important. It was very difficult to study the human microbiome, specifically asking probably these two questions. Who is there? So which are the microorganisms that are colonizing us? And what are they doing? So which are the functions and the reasons why they are there? So recently the field improved a real lot by the use of what we call metagenomics. So metagenomics really revolutionized the field. And this is the approach of studying microorganisms without the need of cultivating every single microbe via high-throughput sequencing, DNA sequencing, RNA sequencing, the thing that we use for the human genome, and we focus on the total collection of microbes in a sample. So without cultivation, we sequence a sample and we try to understand what is the community which is populating that sample. And we need that because if you want to study the microbiome on your smartphone, for example, throw that on a petri dish, and this is what we will get. You can see maybe 1, 2, maybe 3 microbes that are growing there, but we know there are hundreds of microbes there. And we want experiments to really look at all of them. So cultivation can be used, but it's not really helpful to describe the overall complexity of a community for many technical reasons. So what we are instead doing is what is called shotgun method. So let me introduce a bit schematically that is, let's say, framework. So we start with what we call an in vivo microbiome sample. This is just a gram of feces or a drop of saliva, for example. And we collect. So this arrow here, there's a lot behind how you collect samples and how you keep these samples under specific conditions. We are not going to talk about that today, but of course it's a very important step. So once we have our microbiome community, our sample, the important step here is the DNA extraction. So either you want to break open all the microbial cells and free the DNA, so that sequence the DNA. So once we have the DNA pulled out of the cells, of the microbial cells, we can go to sequencing using high-throughput sequencing. This is the main reason why this type of microbiome studies became very popular only recently, actually, where it was really possible to scale with many samples, thanks of course to the huge drop in sequencing cost, which is really clear in this graph. I'm sure it's pretty familiar to most of the informatics people here. So coming back to the workflow, so at this point the experimental part here is finished. We have everything is going to be a computational software. So the first one is pretty standard, if you like. Is the quality control of the sequencing reads plus the decontamination of what we call contaminant. The contaminant in this case is the human genome, not the microbial genome. And then we have what we call the primary analysis. So this is a set of computational tools that aim to go from your unstructured set of breeds to something more understandable or interpretable features, like for example which microbial species are present in a sample and which abundance, which relative abundance, but also which genes, which functions, which microbial pathways are present, and again, and which quantitative abundance. You can also think to reconstruct full genomes from microgenomes. And we do that by relying on a lot of reference information that really needs to be organized. And at this point we have a set of features that of course we can cross reference. We have to cross reference with the clinical data about samples. And here we have something that we can call a slightly more typical bioinformatics sample, at least just from discovery, classification to any other task. And of course we probably need all of these tasks to validate the follow-up evaluation. So metagenomics allows to computationally study not only those well-characterized microbes, but also those ones that are pretty difficult and sometimes impossible to cultivate. The possibility to assemble genomes from metagenomes recently paved the way for large comparative studies, cultivatable and non-cultivatable microbes of different resolutions, including those that to be named still unknown microbial species. So the problem here is that there is still systematic procedure for organizing and processing this large collection of mice, metagenomes and genomes, together with the reference genomes from isolate sequencing and their metadata, which describe their relation with host health and environmental factors. So here is the question. So what if the way we organize the genome also gives us directions to characterize that? So what does characterize mean? It means that we should be able to assign them a name. So genomes are defined based on a taxonomy used to classify microbes based on their kingdoms, for example bacteria, viruses, eukaryotes, phylum, class, order, family, genus, and species, so 7 taxonomic levels. So the main point here that we want to look inside is how we go from the reads to which species they represent. So this is called taxonomic characterization, which is not really straightforward. So one can think that you can just map all your reads against the reference genomes that are available, but it's not really a good idea. Let's see why. If you do that, even for just one genome, for example, the E. coli genome. You break it down to multiple reads and you map them against all the reference genomes in CPI. And what you will end up is a pie chart like this. So only 61% of your reads are mapped against genomes. You cannot even equalize species. But you also have a 25% of your reads that are mapped against the Shigella. And you have many other species here, and one of them is the Cinepestis, which is the culture variety of the bubonic plants. So we use the most used bacteria species, E. coli, strain Q12, and we say that there are some traces of the Cinepestis. That's very bad, right? So it could also happen that we are not able to easily classify a genome, not even at the family level. And in this case, classical taxonomic profilers doesn't have possible at all. What they call a database of reference genomes, and if you don't have the reference in your database, you will not be able to identify particular species, right? So is there a way to easily identify also those previously undetected species in metagenomic samples? That's the question. And the answer is yes. Of course we can. Of course we can. The solution is called meta SPT. That's a scalable framework to automatically organize and index metadata genomes and accurately characterize metagenome assembled genomes with sequence trees. That's the link to the software. It's open source, so we deployed the first release a few months ago. It's there. So before starting describing the framework, I mentioned the Java sequence building tree. So let's see. Let me briefly introduce this data structure. It's a tree data structure. It's a binary tree in which every node is a Bloom filter. So let's see what a Bloom filter is. A Bloom filter is also a data structure. Is designed to tell us rapidly and memory efficiently whether an element is present in a set. So it's able to represent sets. It's probabilistic data structure in the sense that it's able to tell us if an element is definitely not in the set or it may be in the set. It's nothing else than a binary vector with a certain length and whose content is initially set to 0. So let's try to say that it's essentially able to represent sets. So let's say that we want to insert an element. These are the string. This is a string on the alphabet ACGT. And we need a way to encode this string to insert it into the set. So what we usually do is to pass this string as input to one or more hash functions. Let's say that the result of the hash functions is a number between 0 and the length of the root vector. We just need to select the cells of the bit vector for which their position corresponds to the result of the hash function. So the result of the first hash function here is 3. So let's set the substitution to 1. And the result of the second hash function is 7. So let's set the silent position 7 to 1. That's pretty simple. So let's try again with another element that we want to insert into the set. The result of the first hash function is 1, so let's set the silent position 1 to 1. Well, the result of the second hash function is 7, so let's set the silent position 7 to 1. It was already set to 1 actually, so 7 was also the result of the second hash function on the first element that we inserted in the previous slide, so we don't need to do anything else here. One more. The result of the first hash function is 1, set the element position 1 to 1, and the result of the second hash function is 6, so let's set the cell in position 6 to 1. Let's say now that we want to remove an element from the set. Is that possible? It's not. Of course it's not possible. It's clearly not possible because we have, as we have already seen with these examples, an hash function could produce the same result with different inputs, right? So if we set, for example, the cell in position 1 to 0, we are potentially removing a lot of elements. Okay. Let's introduce something different now. We have a string and we want to know if this string, this element, is already into the set. So consider this first example. This is a string we already inserted in one of the previous slides. So we already know that it should be in our set, right? So how could we verify that? Let's take this string, pass it as input to the same hash functions we used for inserting the element. And then produce two numbers corresponding to the indices of the group vector. These cells in those positions are both set to 1, right? So yes, that string may be into our set. What about this other example? We are going to use a string that we never added into the set. So what happens here is that because it happens something interesting. The result of the hash functions produce two numbers, two indices, and the cell under the leucine cell box one, so like room filter staring after, yes, that element may be into the cell. This is still false positive, right? And that's the main reason why room filters are called probabilistic functions. They could produce false positives, no false negatives. And look at the other two examples. There are two strings that we never have with molecular cells. We just need one cell set to 0 under an index resulted from one of the Iasi functions to be sure that the string does not matter to the cell. Okay, so let's come back to the sequence trees now. So we say that it's a three-data structure in which nodes are Bloom filtered. So particularly it is omitted for querying huge amounts of sequence data sets. And it works by hierarchically organizing Bloom filter representations of the input data that are specifically located at the reach of the tree. So in particular, each filter contain the set of keymerts present within a subset of the sequence of its building a tree is also pretty straightforward. It works by organizing nodes according to their Hamming distance versus all the other nodes. This is the first implementation of the sequence Bloom trees proposed by Solomon in 2016. So now that we have a minimal understanding of these data structures, let's introduce the framework, MetaSBT. That's a framework is composed of different modules, different subroutines. So let's start with the first one, which is called index. And this indeed is responsible for indexing a set of reference genomes, usually retrieved from NCBI gene bank. By organizing them following their taxonomic classification. Building also a series of sequence Bloom trees at all the 7 taxonomic levels. Using ODSBT is a software that implements an improved version of the sequence trees in terms of speed and efficiency compared to the first version of the Solomon in 2016. It also supports the quality control procedure and the verification procedure just to be sure that we're not going to have the same gene. So please note that this is going to be to build a multitude of sequence Bloom trees instead of building just a single tree with all the input genes. That's because of a simple reason actually, which is also a big drawback of ODSBT. So despite it's really fast and doesn't require a lot of computational resources, it's also not able to update its tree with new genes. So you may need, if you want to update the tree with new gene, you may need to repeat that from scratch every time we want to add a new gene. So this is the main reason why we don't build a single tree with all the reference genomes. Just because in case of an update, we need to rebuild everything from scratch. It's not feasible, and it will require a lot of computational resources and a lot of time to rebuild everything. We instead create a tree for each species. Then we take the root node of the species trees as leads for building the general trees, and we take the root node of the general trees for building the family trees, and so on up to the kingdom tree. So with this organization, with this decomposition, in case we want to add a new genome to a specific species, we just have to rebuild a single branch of the tree, and not the buttons, making everything easier and more feasible. So MetaSBT provides also boundaries module. So this essentially processes every cluster at all the 7 taxonomic levels and report what we call the cluster's boundaries. So for example, given a specific species, it reports the total number of keymerts in addition to the minimum and maximum number of keymerts in common among all the genomes under the particular cluster. The same applies to all the other 7 taxonomic levels. So the result produced by this model give us
an idea
of the genetic diversity inside a specific cluster. And these results are very crucial for establishing whether a new genome must be added to the closest cluster. We will come back on this in a while. And of course, the framework also provides a profiling model that take a genome and input and try to characterize the genome by querying the database. So since we have different taxonomic levels, different trees, the query is actually expanded into 7 different queries. The first one tries to establish what is called a kingdom. So once we know that what is kingdom, we can query that specific sequence from tree to establish what is the closest phylum, and so on up to the closest species and the closest genome, which is also the closest strain. And we also have an update model, which is responsible for updating the database with new genomes. So for each of these genomes, we run the profile module, which returns the kingdom, the phylum, up to the closest species and the closest genome in the database. And here is where the boundaries are required in order to establish in conjunction with the profiles whether an input genome must be added to the closest cluster. And just by looking at the number of keynotes in common between the input genome and the closest cluster. So in case we are not able to characterize a genome at the species level, we just keep this genome unassigned. And once we process all the input genomes, we can come back on all the unassigned genomes, and we can cluster them all together, and this will end up in the engineering clusters at different taxonomic levels, so species, genera, families, and so on. All without any reference genome at all, so representing all those still unknown microbes. That's pretty much everything about the framework. There's only one problem here. It requires a lot of computational resources in terms of CPU power, in terms of RAM, in terms of storage space to maintain the database, to maintain the sequence tree. So for us at the clinic, this is not really a problem. We have incredibly performance computing structure. We have plenty of storage space. But that's definitely not something you could use download using your life, right? That's such a limitation. If you want to produce something that we hope will be used by as many people as possible. So we have two paths to follow here. The first one is about trying to figure out how to reduce rustic which actually the size of the databases, so that we can load them, software, your laptop, just try to characterize the genomes. For sure, you cannot create your own trees, but that will require a lot of computational resources. But you can at least profile your metagenes, right? And that's something we're working on. The second part consists of integrating this databases into the Galaxy platform. So let me spend a few minutes to introduce Galaxy. So Galaxy, what is Galaxy? Galaxy is an open source browser-based platform for the management and analysis of biomedical data. It's a worldwide community project. There are plenty of research groups that are actively working and contributing to the development of the platform worldwide. It integrates a workflow management system with the aim of making tools accessible to researchers without any programming skills. I'm a member of the Galaxy team at the Cleveland Clinic. Daniel Blankenberg is one of the first developers and founder of the platform since 2005. So most importantly, it runs over access, which is the access transfer, which is the inter-university high-performance computing cluster of the United States. So you essentially have access to computational resources for free if you're running your analysis handouts. And well, if you ever worked on informatics, I'm sure you heard about Galaxy. So let's look at a few numbers very quickly. If you're wondering whether it works, whether people is actually using it. Well, these plots I think that speak by themselves. 2020, we reached over 2,000 publications citing Galaxy. With over 15,000 citations in total. And so there is a main server on which the public instance of Galaxy is running, but it's actually something that you can download and run on your own server and something, with your tools, using your computational resources. And well, the first plot here on the left shows the actual number of public servers that run Galaxy worldwide. It's over 150 now. And well, there are plenty of bioinformatics tools are really integrated into the platform. Generally, tools are hosted on the Galaxy solution, which is a repository of tools, actually wrappers for existing tools. And yes, we reach now about 10,000 tools wrapped and ready to use in the Galaxy. So let me also quickly mention every year there is a Galaxy Community Conference somewhere in the world. It's a unique opportunity to network with people who are actively involved in the development of the platform, but also with people that are simply interested in just integrating their analysis tools, so their workflows on the platform. The last conference has been in Brisbane, Australia. This year, the next year will be in Czech Republic, 2025 again in the US, then somewhere else out of the States. They always accept proposals to, propose a new location for the next UCC. We could to propose Rome, but something we could discuss maybe later. Okay. So we talked about we got an introduction about galaxies. Coming back to MetaSBT, we are also building a tool suite for Galaxy that comprising a tool for indexing genomes and thus building a database and also updating it. In addition to another tool for profiling genes. So this is under development, and we will release this very soon. Some results. At the moment we are reading the old viral reference genomes and metagenome assembled genomes from NCBI gene bank and the metagenomic gap viruses catalog for a total of over 200,000 viral genomes. So we started with viruses just because of their size of their genes. They are so small that you can build a database and test all the framework features very easily, very fast. So we use the database that you can actually download. It's pretty small actually. So they are just viruses. I certainly sent a few more numbers here, but anyway, a bit over 40% of the species clusters do not contain any reference genes. So we're talking about over 20,000 new species. Still unknown species. So we are currently updating with the database with other viral mats from other public resources.
And
we also started indexing all the roughly 40,000 bacteria and archaea species from a situation. The idea here is also to build a database with bacteria, archaea, and other chemicals. So concerning this side, we also retrieve the representative genomes of the unknown species level genes, SGBs, described in this paper. So here the authors use what they call species level genome beans to hierarchically cluster genomes according to different thresholds. Three thresholds in particular. Using 5% of genetic distance to define species, 15% of genetic distance to define genera, and 30% of genetic distance to define families. With MetaSBT, we are instead trying to dynamically define cluster-specific boundaries, right? So this means that at the species level, for example, every species can potentially have its own boundaries. Again, defined as the minimum and maximum number of genomes in common between input genomes, between all the genomes under a particular cluster. And this allows to essentially work independently from the kingdom, while SDBs have been defined specifically for bacteria and archaea. Also, the SDB system doesn't index genomes at all. It would take really long to profile a genome since it relies on pairwise distance between input genomes and database. So these are the main differences with our competitors, I would say. And the way we organize genomes can guarantee an improvement for sure in the accuracy of the characterization of genomes, and for sure a great speed up that allows to scale up potentially millions of microbial genomes. So we are planning to use this set of genomes to validate procedure on bacteria and archaea, and to check how these genomes are clustered with the SDB system compared to how we cluster the species. A few additional feature directions. So we are planning to expand the database with all the reference genomes and CPH. Also considering genomes from other microbial kingdoms. So of course, we are also planning to expand the databases with new max, genome assembled genomes from public medical samples from different organisms and environments to greatly expand the genetic diversity in our databases. We are also planning to host our databases on the Galaxy CDN classes with distributed file system on Galaxy, so that just to make them accessible to every Galaxy user without the need for users to download the databases. Try to build a community that hopefully something constantly increasing collection of new microbial genomes. We are also planning to build a custom Kraken database. Kraken is a quantitative profile data format for medical samples. That would be actually extremely easy at this point. It will unlock the quantitative profiling of unknown species in metagenomic samples. So our plan here is to build custom databases for Kraken and profile as many human metagenomes as possible related to different kinds of diseases and conditions in a case control scenario. And check, whether the difference in the abundance of unknown microbes in case and control samples is statistically significant at that particular condition. And this could potentially lead to the identification of microbial biomarkers, hopefully. So we are also working on the development of a new method for to define cluster-specific filter sites. And this will drastically reduce the storage space required to build and maintain specific filters. Well, software databases are totally open source. They are available in GitHub. Here. If you're working on microbiome, you have some samples which you want your tools to know what kind of unknown microorganisms are there. Get in touch, and that's pretty much all.
I have two questions. My first question is that you had mentioned that Bloom has this problem of false positive, correct? So has that been taken care of while you were designing the meta SDK?
Sure, that's something you could modulate by choosing a proper Bloom filter size, but exactly right. And that depends on the total amount of keynotes your data set. You have your set of keynotes. Before building the tree, you have to establish how many unique keynotes of a specific size, of a specific length are inside your data set. And you could use that number to define the filter size. The problem is that all the filters in all the sequence trees of the database must have that specific fact. And these vectors are going to be very sparse. Because schemas that are in a specific species maybe are not in another species. So you're going to be very fast. There are compression methods that reduce the size, of course. That's not the final solution, because the size of the database is really huge. Not in case of viruses, but in case of bacteria and even if you consider fungi, for example, which the genome is way bigger than viruses, bacteria here, and a proper human length is around over 30. But again, that's what that says. So the total amount of unique keynotes is going to be really large, and thus the length of the bit vector is going to be huge. The bit vector is going to be very sparse. So we need to find another way to reduce drastically reduce the storage space. And that's what I was mentioning. We are working on another possibility to establish clusters between different sizes. That's in development.
So I think that the choice of the Kimmer sites affects the number of false positive. Yeah. So how do you set these sites of Kimmers in order to you have to find a balance between the space you need and the probability to find some false positive.
The size of Kimmers are established with software like Kimmer or they use some statistical model to try to establish how many keynotes are in the data set, genome and data set genes.
But you cannot know a priori which is the best.
You cannot know that for sure. So you essentially get all the keynotes that are present in your genomes. And you establish a number of keynotes that appear plus one or two times, because that will be offered sequence together, right? Yes, and you use that number. We actually use that number increased by I would say 20%. Just because otherwise we could saturate these Bloom filters very fast when we are going to update the data.
So you have a very, very different number of the sites among several clusters.
Correct. my side. Do the hash functions also play a role in this? For setting these blue filters, how many you have, whether it's part of the system design them, or they just take them as branches. So we don't use cryptographic hash functions, right? We need hash functions that are as fast as possible. We don't actually care about the number of collisions because we are going to use multiple amount of hash functions. So we could take that under control by increasing the number of hash functions. So we just need a hash function that is as fast as possible. But is there an element of the design of the system? Like you design the proper number of hash functions. How many do you need? No, it's two. Just two. If you increase the number of hash functions, it will be really fast. The overall amount of time required to build the filters, just to build the sequence. Also the collision. And have you ever considered a sort of automatic tuning for the type of hash functions? Would that make any sense? Could be interesting to investigate that, but I never considered it much because let me understand something better. Eventually, you would need to have a given hash function, a given hammer size, or bacteria, another one, or you aim at having only one for everything. Like one. I don't think that. I mean, the number of tables that you set and the blue filters that you use. Are they general throughout all the analysis that are done by the SPC, or customized on different things? It's specific for that specific team. So these, I built a database for viruses. The proper human size is 9 millimeters. So we have a specific amount of keywords for our set of viruses. For bacteria and archaea, it's a storage. They usually use 21, but again, it depends on the data set and for fungi it's even bigger, around 30 or 33. The bigger is the tumor size, the bigger is the blood flow, the bigger is the pathogens. And the storage required also. But the paper size is not something that you decide. I mean, it comes from the data that you human size is something that we decide actually. We need to establish the proper human size for that particular data set.
Given a data set, you can find then you don't know a priori which is the best.
Using the tools.
You had to.
Yes.
You
mentioned very fast the deletion program on Google. Do you really need deletions?
There
are some solutions
that allow to the track of the frequencies of the element filter. We don't need that.
There's a filter basically hashing, right? So it's using the technique of hashing. So if you want to remove something, I don't know how this hashing. Generally, we talk about hashing. If we have chaining, to avoid collision, we have chaining. So if you have the chaining factor, we can, if we use that, we can remove elements from hash table.
You have to select every.
You need to go through all the elements that you previously set.
It's like you build it from the beginning.
Yes.
Okay. Any other question?
online questions?
Online questions?
No.
No.
Ok.
Okay, so we thank again for
Grazie Fabio.
Bravo Fabio.
Molto bello.